Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Rui-Ting Huang today. Rui-Ting is graduating from the University of Illinois at Urbana-Champaign, where she's one of Mark Hasegawa Johnson's students. She was an intern here in 2009 and did some very interesting work with Zhao Li at that time. Basically, they did language model training in order to maximize the mutual information between the acoustics and the language model when all you have to start with is the language model itself and a phone confusion matrix. From then she moved on to work on her thesis work, which she's going to be talking about today, and that focused on mixed supervised and unsupervised training or semi-supervised learning, and she'll tell us about that now.
So thank you, Jeff. So today I will talk about my thesis research on semi-supervised learning for acoustic and prosodic modeling in speech. So I will first give a brief introduction, brief background on semi-supervised learning. Then I will present two kinds of problems where I investigate the use of unlabeled data by some proposed semi-supervised learning algorithms, followed by some conclusions. So we know that the scale of audio data, sorry, actually there's a sequence here. So that's the talk outline. And so the scale of audio data that we can collect is increasing dramatically these days. It turns out that speech data without transcriptions is easy to collect but time-consuming to transcribe. This motivates the research on semi-supervised learning, which tries to use unlabeled data in addition to a limited amount of labeled data to improve the supervised model. So the ultimate goal here is to improve speech applications where recognition performance was limited by the amount of transcribed data. And there are a few related methods proposed for speech applications. Most related approach can be categorized into self-training methods, which we conventionally call unsupervised or some slightly supervised training with confidence threshold, meaning that what it does is that for untranscribed speech, we run an existing recognizer and on this set of untranscribed speech and augment the training set with confident enough transcription, automatic transcriptions, and retrain the model. While it has shown demonstrate the potential use, demonstrate the power of untranscribed data to improve the system. There's no systematic way. There are some drawbacks. For example, there are no systematic way to determine the threshold of confidence measure. And on the other hand, there's no theoretical foundation about the convergence property. So in my work, I'm taking another perspective, trying to propose a principle framework that we can train our models by some reasonable training objectives, considering the influence from both labeled and unlabeled data. So let me give a formal definition of semi-supervised learning, meaning that we know that in machine learning, the classification problem is given the data described by some signals, some features, we want to map it into one of the predefined class categories, which is called supervised learning because we would need a training set of label tokens, and then we learn the mapping from them. So semi-supervised learning meaning that in addition of those labeled tokens, we are also given a set of unlabeled data to learn the mapping. So in our framework, the models I'm looking at are either Gaussian matrix models or hidden Markov models. So by learning, I mean the estimation of GNM or HNM parameters. So the basic idea is to use unlabeled data to generate the applicability of classifier for unseen data. There is a prerequisite though, which is we assume the distribution of unlabeled examples is relevant for the classification problem. So in this way, we can because if we have a large quantity of unlabeled data, we can leverage the data distribution from the unlabeled data and connect it with the classifier. And there are different perspectives that we can use to make use of this connection. One is that the first kind is kind of treat unlabeled data in the context of missing data problem, meaning that the unlabeled data is kind of like incomplete data, misses class label information. This incomplete data can be, one way to treat it is the EM algorithm. Another kind is we trying to impose some measure of unlabeled data to regularize the overfitting problem caused by using labeled data only. So in the following, I will my method is basically based on these two perspectives. One of these two perspectives.
So on the prerequisite, what is how do you measure the relevance? The distribution of unlabeled samples is relevant. How to measure the relevance?
There is no quantification on this relevance. By relevant, I mean that, for example, if we treat the, as I say, if we treat the missing data, if we have a generative model, then unlabeled data is relevant here because generative training is going to find the better likelihood to describe your data. Then in that case, it's natural to incorporate unlabeled data into your generative training. And if you have a better generative classifier, generative model and which you are using for classification problem, then they are relevant. Yeah, so, and also by, there are another relevance. For example, here, if we think the distribution of the unlabeled data can change our thinking about the model we learned from only labeled data, which I will show later, then it's also relevant. Yeah. So I think the point I raised here is that it's not necessary that unlabeled data can help. You need to have a correct context, correct model to use it. So, so in particular, I propose a training framework where speech models are trained to optimize an objective that reflects reasonable assumptions about both labeled and unlabeled data. And in particular, there are two kinds of training criteria. The first kind is generative training criteria, and we will find its ability to discover unseen class. And we apply this ability to the problem of prosody break detection. And then I go on to the acoustic modeling problem and propose a semi-supervised maximum likelihood criterion for GNMs or HNM training. And then the other kinds of training criterion is regularized discriminative training criterion, meaning that the original discriminative criterion will be augmented with a certain measure on unlabeled data as regularization. And I will apply it to acoustic modeling. So the first part I will show how we use generative model to deal with detection of prosody in Mandarin speech. So prosody, let me briefly introduce prosody. Prosody are those variations in pitch, loudness, tempo, and rhythm in human speech to convey extra information in speech communication. There are many prosody events across many languages, and here I'm interested about prosody break or prosody boundary, phrase boundary, meaning that instead of speak an utterance in a flat tempo, we usually will tend to pause in several locations within an utterance, and the boundaries between those boundaries between natural group of the words in speech is prosody break. Here is an example in Mandarin speech, where each symbol here represents a syllable corresponding to a Chinese character. So now I play this male speaker, and you will find that instead of he speak it in a flat tempo, he will try to slow down slightly in some place, as I will indicate by a blue line.
打电话给邻里两人，约好交货时间地点。
So those blue lines is the part where the prosody breaks are. Then locating those prosody breaks natural group. I'm finding my mouse. Locating those prosody breaks in speech is useful for finding natural group for speech synthesis, and also it appears that the segmentation according to prosody corresponding to syntactic structure in speech, and which can be used for speech understanding. Furthermore, we could also have build prosody-dependent acoustic modeling, meaning that the acoustic model will change depending on the prosody event currently. So since it's useful, we are interested in the task of automatic prosody break detection, which is essentially a classifier which receives acoustic correlates and classifies the event as non-break or break. And because it's a classification problem, supervised learning problem, and which will require the prosody label data, we will need the prosody annotation, and it's usually done by linguistic experts who are sensitive to those acoustic cues, and then and can be efficient to mark those prosody marks for corpus. So because it's even more harder than word transcription, which motivates our goal, which is to automatically locate prosody break in Mandarin speech without any prosodically labeled data. It can be done because of two things. One thing is that we will first identify reliable representative from the non-break class using some simple textual lexical cues for Mandarin. Then, given a small set of labeled data, we rely on semi-supervised algorithm to learn a classifier using both stable and the rest of the unlabeled set. And it's worth noting here that here we have a special setting of the problem where the labeled data is only available from only one of the two classes. And we will see that we are able to take care of this scenario and find the unseen class, the break class, by our algorithm. So here is an example how it works in general, meaning that if we have utterances, then the speech recognizer will generate text, recognize text for us. In here, it's a character sequence of Chinese characters. Then for every syllable boundary here corresponding to each character is where we need to decide if there is a prosodic break or not. And according to some rule, which I will explain later, we are able to identify some class representative for the non-break class, I indicate as MB here, and we collect this data as a label set. The rest of the syllable boundary with unknown class identity go to the unlabeled set. Then our semi-supervised learner will use these two sets to estimate a possible underlying model and predict the most likely prosody for those unlabeled boundaries, or even a held-out test set. So let me show what the rule is. To find the class representative, we leverage some information from the text, which is output from the recognizer. And before showing the rule, let me introduce the concept of lexical word in Chinese, meaning that beyond the single character, the lexical word is actually the combination of multiple characters which can convey different lexical meaning than its character components. It's reasonable for a recognizer to output a word sequence rather than a character sequence. For example, you can have a word-based language models. Then the lexical cue we are relying on is a literature study that prosody breaks do not exist within a short lexical word. By short, we mean the lexical word contains less than 3 or equal to 3 syllables. Then, so we see that according to this cue, for those within word syllable boundaries, we are pretty sure they are from non-break class. So we mark them as MB. That's how we found the class representative. And the rest go to the unlabeled data. Then how do we learn from this mixed set? First, let me show the generative model we are using, and I show how do we train the model. So we are using a mixture model, a tight mixture models that has n mixture components that can generate data x, y, I sub n. X is the multidimensional prosody features containing n acoustic correlates. Y is the class information, and I sub n is the indicator of label is missing or not. So then the joint probability of the data is described in this mixture-based model, where we have a weight and a Gaussian for each component. But because it's a tight mixture, two classes, meaning that two classes share the same pool of Gaussian components. So the class discrimination comes from the soft class membership defined by this component-dependent class probability. Also, one important feature here is that we have a class-dependent label missing probability to match closely to the one class scenario, meaning that if we have known that from the training data we don't have label information from the break class, we simply apply the constraint that the label missing probability for the break class is 1, and then we learn the rest of the parameters. So because it's a generative model, it's natural to have a maximum likelihood training criterion to estimate all of your parameters. And the likelihood is computed by the combination of a labeled set and the unlabeled set, and it can be solved by EM algorithm. Then the classification is simply finding the class that maximizes the class posterior probability, which can be computed in the following way, using the parameters we just learned. So we show our we evaluate our unsupervised approach in a duration corpus, which is a rate speech by a single male Mandarin speaker, in this corpus, prosody annotations are available, but we just use it for as a ground truth for evaluation. And there are two kinds of break labels, two levels of break labels, but we treat them as the same break class. Then regarding features for each syllable boundaries, we extract 8 acoustic features, including pitch, duration, and energy-related features. Yeah. So here.
Is there some reason why it was just one speaker?
Yes, it's just one speaker.
Why? Why not use?
Because this corpus just contains one speaker.
Does that make a difference?
It makes difference because then we will need to take care of speaker normalization regarding the prosody features, and it could be eliminated to some extent. But now it's a simpler situation.
Regarding break, I think you can observe whether there is some silence inserted between the words, and use that kind of thing as a feature.
Yeah, sure. So yes, I totally agree with you. And one thing is that we observe this thing. We also observe this fact. However, the number of silence, the cues, the number of locations that can be identified by silence vary depending on the corpus. It's not necessary to have sufficient number of syllable boundaries marked by silence. It depending on the corpus. So we think identified class representative from non-break class is more general than finding the boundary by silence. Yeah. But it's possible. It's possible to add in those data by silence, and then we are back to a normal setting of semi-supervised learning where the label set have information about 2 classes. Yes, actually, I have that result, but I didn't show here for a complete comparison.
See your previous slide. Classification. So it's a classification. You know the word and you classify it.
Yes, in this case, it's a prosody event classifier. So I know the syllable boundary. So meaning that yes, they are all. I assume that I gather information from the recognizer output.
So for more complete modeling, you may need also, doing a sequence decoding.
Yes.
And also maybe using language model. Word-specific boundary information is there too.
Yes. So, so I will show that for acoustic modeling, there is a sequence model. But here for prosody modeling, I haven't considered the sequence scenario yet.
Did your transcription come from a recognizer or there is a ground truth?
So in the experiment, the transcription comes from the ground truth.
Okay. You didn't think about whether there is some mistake in your transcription?
No. Yes. And another thing is it's and maybe we can discuss it later. So okay, so I want to show demonstrate the model's ability to discover a new class by using one of our features as an example. So the feature here is the difference of averaged energy of the syllable after and before a syllable boundary. The topmost plot is the histogram of the features in a training set, regardless of the class information. The next two plots are the respective histograms for this one is for non-break class, this one is for break class. We see that the break class has a lower mean than the non-break class. Then we show the estimated data distribution given only a subset of labeled token from non-break class with different number of Gaussian components. And we see that if we have sufficient number of Gaussian components, like 16 Gaussian components, we are able to identify this is the joint probability I computed using the model. And we see that given the sufficient parameters, we are able to identify the contrastive class that we haven't seen label set before. So let's look at the detection accuracy results. So let me show two reference numbers first. By fully annotated approach, I mean that assume all of the labels is partially label are available. So this is kind of the upper bound performance we can get, the 91%. And then by translate, I mean because the good class distribution of the data, if you simply assign every syllable boundary as non-break, we get 77 accuracy. But it's not a reasonable method according to the precision and the recall. Then by using the non-break data in the label token, we are able to given a reasonable accuracy, but it's more meaningful to see that we have a reasonable precision and the recall summarized by F-score here. So short summary is that we are able to discover partial breaks by a tensor Q and a semi-supervised algorithm. Now, we now move to the problem of acoustic modeling, and we will start with generative approach that has shown its effectiveness in prosodic model. So, in the context of acoustic modeling, with the generative criterion such as maximum likelihood criterion, unlabeled data, it's all GNMs or HNMs are all generative model. Given this context, unlabeled data can be naturally incorporated into generative framework. That is, we extend the semi-supervised version of ML criteria. In particular, the model parameters will now aim to maximize the likelihood of the joint label and unlabeled set. And it can be done by EM or Bound-Welch for GNMs or HNMs. There are some issues here. First, raised by Cohen. That is, incorrect model assumptions can cause unlabeled data to degrade performances. But in their paper, they assume one Gaussian distribution per class. In our case, we're using a more expressive probability model, which is GNN, and it's already a better model assumption than a single Gaussian distribution, and we don't observe the degrading effect so far. And also, it's well known that generative model may not optimize the classification accuracy well, and as people usually go on to do discriminative training, we will see how do we extend the supervised discriminative training to semi-supervised version. So, the discriminative criterion is simply if we are using maximum mutual information, it's finding the maximum of the average log posterior probability. And since discriminative training is prone to overfitting the training data, it will be helpful to include an regularization term to reduce the problem of overfitting. Then our semi-supervised algorithms are essentially using certain measures on unlabeled data as regularization to the supervised training criteria. Therefore, we propose to, there are two regularization measures. The first one, we propose to augment the supervised AMI criterion with the maximum likelihood measure on unlabeled set. The interpretation here is it's balance between leverage evidence from the labeled data and also clustering information from the whole input data.
So, can you go back to maybe one more? So isn't there a prior on the label sequence, a prior on YI that needs to be in there somewhere? If you look at the mutual information with probability of X and Y over the probability of X by itself and the probability of Y by itself, and then use the chain rule and you have the probability of X and probability of Y given X, and then the P of X cancels in the numerator and the denominator, so you have P of Y given X over P of Y.
I think I don't follow you, so.
Maybe she just hasn't done that expansion, but maybe this is like what it is, but then you could expand it P of X and Y. No.
What happens to the P of Y? Isn't that the denominator?
Does it matter?
Yeah, it's if you.
Well, but for discriminative training, P of Y is.
So.
Yeah.
So here it's for the it's the classification version of the criterion, and yeah, I think as you said, there is a denominator, there is a P of Y term, but
Well, I think Y is a label, right? And that's
Right. Yeah.
I just think it's missing. I think you could expand that into P of X given Y over P of Y, but I just think it's a problem.
yeah, I think.
Well, let's keep going.
Yeah, I have to say so I will look at the classification case and the recognition case, and this is the measure that I use for the classification training, and I think it's generalized to the AMI the AMI criterion for the recognition.
Is that different from conditional maximum likelihood?
This one is actually conditional maximum likelihood for classifier. We usually call it that. And I'm just saying that they are equivalent if you generalize it to maximum mutual information for the recognition case. So I first talk about the hybrid training objective. Then because if you look more closely at the estimation problem, the objective is actually composed of multiple terms of likelihood, and the corresponding parameters, parameter update formula can be derived based on a modification of Gauss transform or extending Bauer-Welch. So essentially, it's a modification of original MI training by adding additional statistics from the unlabeled data, like this way. And the L and the U is just the normalization due to the amount of the training data. Alpha is the balancing factor. So this is the version for classification where each model is represented by a Gaussian mutual model. So this is the mean vector for class C and the M component M. So I want to discuss first the relation to other work. So there have been several techniques have been developed to mitigate the overfitting problem. For example, H criterion globally interpolates MI and ML objective, and also I-smoothing is used to interpolate with Gaussian component dependent priors based on the ML estimate. Our criterion is different in that we leverage information from unlabeled data. And there are different interesting perspectives proposed by IBM researchers in this year, ICAS this year. They proposed a maximum entropy measure on unlabeled data to augment with the supervised MI term, which essentially results in a minus term here, minus sign here, flip the sign here for the unlabeled measure. So
Must be wrong, yeah?
so I haven't come. They have slight improvement, but they combine that method with another paradigm, which is multi-view learning by combination many systems. So I mean, it's interesting to try what I will get if I flip the sign.
So in words, correct me if I'm making a mistake here, but I think in words what the first one means is that you want to maximize the likelihood of the supervised data and make sure that you've got a hypothesis of unsupervised data that gets high likelihood. Mm-hmm. And what the second one does with the minus is you want to maximize the likelihood of the supervised data while saying as little as possible about the unsupervised data. Did I get that qualitatively right?
Yes, and I'm thinking if you have very strong supervised model, maybe it's reasonable. I mean, maybe you can try to use unlabeled data to penalize the likelihood on the competing hypothesis as a penalization. But here you will see that in my experiments, I assume we have limited amount of labeled data, meaning that my supervised model is pure in the first place. It is poor in the first place. And in that case, I rely on the unlabeled data to capture the data distribution. Then in that case, the hypothesis, regardless of the, it might be some errors in the hypothesis recognized by recognizer, but in that case, in this context where I don't have a good enough distribution model in the beginning, maximum likelihood regularization might help.
I think if IBM, if they use -1, that means they don't want to have any impact from the unlabeled data. So what's the usage of the unlabeled data? We need to train a model, maximize the likelihood of unlabeled data instead of
I agree with you.
minimize it. Yeah.
Doing the minus seems bizarre.
Yeah. I'm really wondering why they use a
Here
minus.
there's a minus in front of it.
No, wait. It might not have been
Only
minus in front,
minus.
because in the entropy there would have been a P of there would have been y involved. I mean, wouldn't have been.
It's p log p and approximate by the likelihood there is no p. The
Right.
data.
No, it's not a class entropy. It's just entropy of the data.
It's just.
Right. I mean, it's p log p.
I was thinking about p log.
Maybe you can.
I was thinking about p log p. I was assuming that was what they would have done.
It's just like this.
Right, but there's still not a y in there.
There's no class information here. And yeah, it's just
But
like,
to compute P of X, you have to hypothesize class information, right? Because you have class-based models.
yeah, you have to.
You're going to have to break that down into somehow a sum over all the possible class labelings and then the conditional.
Actually, I have.
Probability, I think.
Actually,
But keep going. Yeah.
Yeah, I use, as you said, to approximate it, usually you rely on the prior information here. Yeah. So I think they do the same thing. They use a language model and their acoustic model to approximate this. Yeah.
So here in this equation, the first line, on the unlabeled data, if you find some theta that gives any of few p of theta, of x, very low probability, then your maximization will get hugely penalized. So you would not allow, those densities that gives very low probability, very low likelihood. So does that help to explain why it helps, why it,
Yeah.
So you try to make the, for every, for the xi, you make them almost equal, basically, likely.
I see.
Is that kind of smoothing towards average?
I'm wondering if there's some kind of self-inconsistency, like if you have a pile of labeled data and no unlabeled data, you maximize the probability of the labeled data. And now imagine that you chop your labeled data in half and move half of it into the unlabeled data and throw away the labels. But it's the same data. So you drop the probability of that same data that used to be trying to improve its probability, now all of a sudden you're trying to decrease its probability. It seems kind of inconsistent. But
So that's interesting, and I think they also think it's kind of corresponding to the maximum entropy idea. So I think it's worth discussions. I already talked about this. Okay, so the second regularization I have is conditional entropy regularization, which is the uncertainty of class prediction given features. The paper first proposed this idea is based on the assumption that unlabeled data are beneficial, especially when classes are well separated. Then you are trying, if you have a model prior that when they estimate a model, they apply a model prior that prefers minima class overlap, which is equivalent of minimizing label entropy on unlabeled data. The interpretation, the other interpretation is that the negative conditional entropy term encourages the model to have the greatest possible certainty about its labeling decisions. So it reinforces the confidence of the supervised classifier we learned from the labels. So to compute the conditional entropy, because we don't know the real data distribution, we approximate it with the empirical distribution from the unlabeled data. So the formula is essentially like this, and meaning that we have a discriminative criterion for labeled data and the negative conditional entropy for unlabeled data. And it's in a sense an unlabeled version of discriminative criterion. So we have a coherently discriminative objective. Then we cannot use, because of this term, we cannot use the extending bar wheel. So we optimize it by gradient-based methods based on the gradient computation of this term. Moreover, we use preconditioned conjugate gradient method to accelerate the convergence rate of steepest descent. So this I'm just showing the gradient of overall is the gradient of these two, which looks like this in the classification case. Then I.
You may get to this, but I'm going to forget the question, so I'm going to ask it. At the end, you're probably going to compare results using different techniques, and one of those techniques is going to, not the optimization, but one of the techniques, maybe it's just plain ML, which presumably you've used EM to optimize. Then there's going to be this other technique where you've used the preconditioned conjugate gradient descent to optimize. And there's going to be a difference between those two techniques. And so the question is, how do you know that difference comes from the objective function versus the optimization method? Like if you did preconditioned conjugate gradient descent for the regular maximum likelihood objective function, maybe that would give a different answer.
I see, but
is there some reason you can tell me, oh, you don't have to worry about that?
I think as long as I'm sure the objective functions are optimized, so all of them.
All are going to get local optima.
Yeah, either of them just getting local optimum, and
so maybe
I think
optimization technique is more likely to put you into a better local optimum than another one.
I see what you mean. So for example, for this method, I plot the training objective, and then it looks reasonably saturated after several iterations. I haven't tried to do the same thing for the EM algorithm, but it usually, but I assume that it actually converges very fast, right? But I cannot comment on if the preconditioned conjugate gradient is better than finding. I think the nature of them are the same, finding local maxima. None of each are finding better local maxima, and so I guess they are fair to. So it's fair to compare them. I think because the way I use preconditioned conjugate gradient is to speed up the training. I'm not aware of any optimization property of it that can help to find a better local optima. So
different kind of optimization methods may be just converge to the same local minimum. Otherwise, you need to some advanced method to jump out some local minimum or maximum and then get some convergence to another one. Otherwise, usually this kind of thing just converge to the same.
I disagree.
Disagree?
I disagree.
Okay.
Because this is the whole reason why people have like inertia in their gradient descent techniques, so they can get over these local minimum. It really depends on how you follow the gradient, where you're going to end up.
I think, for example,
if you look at a different field like neural nets, people put a huge amount of effort in exactly how they're going to optimize these things and what the learning rate is and whether they precondition or don't precondition or what the starting point is.
Okay.
And even though the objective function is
point,
and even though the data is the same and the objective function is the same,
the details of the optimization, at least in that case, seem to make a difference.
Well, let's see how much better her results are, and then if they're really good, we can start thinking about whether it was the optimization or the,
But
or the others.
one thing is that at least for AMI, I compare with gradient descent method and the extended Bound-Welsh method. They give almost the same number.
Oh wait, what? Who did that? When?
I did that. So I mean, without the negative, without that term, if I do that with gradient descent method, I have the same result with the one that I optimized using extended Bound-Welsh.
Okay, so that's evidence. That's what I was asking.
Okay.
You've done that. So you have done that.
Yeah, I've done that,
Okay.
but yeah, for AMI I've done that,
Right.
but it's similar because extended Bound-Welsh is the extension of Bound-Welsh, so probably it provides some evidence about the optimization. Doesn't matter much here. So I'm just saying that yeah. So it's a negative conditional entropy. It's different from the previous interpolation term, and then the negative conditional entropy has been applied to other discriminative classifiers such as logistic regression and CRF. And here we apply NC regularization to discriminant training of GNMs and HNMs. So I look at two specific tests. One is classification, the other is recognition. Classification is probably I don't need to explain more, but I'm assuming I already given the segment. I just want to recognize the phone identity by the posterior maximized posterior probability, and which has a component that is a phone dependent distribution described by Gaussian mutual models. Then I use Timmy corpus and to create a semi-supervised setting. Labels of a certain percentage of training set are kept, and the rest of unlabeled set becomes the unlabeled set. Then I extracted segmental features for each segment, which is a fixed length vector calculated based on the PLP features. PLP features within the different regions within the phone segment, and also pre and post the segment, and plus the log duration. So this is I'm showing that it has, so I think the label is not clear, but the blue line is objective value, and we have saturated in 50 iterations, and the green line is the phone accuracy. I calculated on the 11 set. So you see, it correlates well. It's not exactly the same because it's not training set accuracy. It's kind of test set accuracy, but still, regularization helps us to have a nice correlation between accuracy and the objective. Then here we show the classification accuracy for two regularizers. One is ML regularizer, the other is conditional entropy. The axis is the decreasing amount of labeled data with increasing amount unlabeled data. Therefore, the baseline performance, we can see, which is the dashed line here, decreases along the axis. And to have a clear view, I subtract the supervised model, the performance of supervised number, with two regularization approach. And you can say they have very different behaviors. The ML regularization helps very much for the case where we only have 20% of labels available. And this is the rightmost number is 5% of labels, so it outperform the conditional entropy regularization given very limited amount of label data. On the other hand, a conditional entropy regularization consistently improves over MI training, regardless of the supervised the quality of the supervised model.
Was it only alpha that you used, or like there's some kind of term, right?
It's I have let me show it. Let me show a graph very quickly, and see if I can go there. Wait.
If it's difficult to find, you can just tell me.
No, it's just alpha is between alpha is at the range of 10, and I have a plot showing that it's quite insensitive to so the performance is insensitive to the value alpha. So
does it change when you use less or more label?
So it's not changes much. No. I want to show that. Let me see if I can. Very quickly. So I have the labels, few labels to more labels. You see that they have the similar behaviors by tuning the number of alpha. Okay, let me go back to. Okay, then about phone recognition. Now the task is to recognize the whole phone sequence given an utterance. And we know that the recognition will be based on the score from both language model and the acoustic model. And
go back one. And this, or maybe even one. I just missed in your setup. So when you have in the MMI only case, that's just training with whatever labeled data you have.
Yes.
But in all cases, it's the same size model, or you're using like a smaller model or smaller?
This
is a GMM training?
Yeah, yes.
So is it like fewer Gaussians? Do you change the number of Gaussians, or is it
Oh,
the same
no,
number of
no.
Gaussians?
The number of the parameters are fixed. Even I'm adding unlabeled data.
So in all the data points in that graph, it's always the same number of
Yes. Yes. Yeah, I will show that actually by adding unlabeled data, we are able to grow the number of parameters by generative training, and I will show that shortly. Yes. Okay, so in the current context, we were interested in optimize the HM parameters for acoustic model. And first of all, let me go back to the generative training I mentioned in the first place, where I have maximum likelihood criterion for both labeled and unlabeled data. And to approximate the distribution of the xi, I have a confusable set respect to each utterance xi, and which is derived by recognition. And in the real implementation, it's essentially can be summarized. Let's summarize by a denominator model. But let's in the same sense, this one is also summarized by a numerator model, encodes the full acoustic and language model used according to the label phone sequence. And for unlabeled data, we have a recognition model used such that it approximates the distribution. Then essentially the update formula for example, one of the mean vectors in your state model looks like this, where we just adding the occupancy statistics from the denominator lattices for unlabeled data. For discriminative training, we have to find a way to compute the conditional entropy for each utterances. Here we approximate it with the n-based hypothesis. So now HI is actually the n-based hypothesis produced by running recognizer on each utterance I. Then we apply the same optimization methods for finding discriminative training. So here show the result. Here we assume we only have 5% of training set available, and the unlabeled data is the rest of 95%. And I compare with the self-training methods, meaning that the conventional unsupervised training way, where we just find the confidence enough transcriptions to add in the label set, then we train the model. Then we see that the best number of Gaussian we can get from this amount of labeled data is only 8 components, and then by adding unlabeled data, we are able to grow. And we see that the semi-supervised learning is slightly better than the self-training ML. And another advantage is that we are not necessarily using confidence measures here for our methods.
Was this with monophones or triphones?
It's monophone. The second result is for discriminative training, where we starting with the initial model as the base model we can train from the semi-supervised generative approach from this graph, from this plot. And then I also compare with the self-training AMI, and as we can see, again, the confidence measure have to use to try for this. And as you can see, semi-supervised AMI is better than the self-training AMI. But it's worth mentioning that when I just use n-based to compute the conditional entropy, it has its limitation in that I only have a few competing hypotheses associated each utterance. It's suboptimal to approximate the sequence distribution. Okay, so some take-home messages that we see that unlabeled data are useful for finding more accurate distribution or a better classifier depending on the training criterion. So for example, we find that in Prosodic modeling, we are able to find more accurate likelihood functions and corresponding to true class distributions, and so we are able to discover unseen classes. And by applying unlabeled data under the regularized discriminative training framework, we can have a better classifier. And one advantage here is confidence measures are not necessary in our framework for unlabeled data to be useful. But of course, you can combine this with try to filter out your data, and by some tuning, you can get better results. And one current limitation of my thesis work is that I only have experiments on teaming set, and it's worthwhile to try on the large vocabulary data set to see how can it be generalized. Thank you. So, any questions and comments?
We have time for 1 or 2 questions.
So in the self-training approach, you use the confidence to select the data?
Yes.
So there's this kind of theory, right? If you select high confidence thing, then the transcription will be more reliable, but you are adding the data which you already know very well, right? So what is your thinking about this in using confidence alone to select data? Maybe for those speech segments, unsupervised, you're not confident about, but they may give you more information, even supervision signal is not that accurate. So how to find this balance?
If you are using the confidence score, I found the similar conclusion as you. For self-training, I would get because I need to try different value of confidence to see which one gives the best performance on the development set, and it's like if confidence threshold is like if this is the accuracy on development set, it's kind of like this. So I usually find something like here, and I think it's we need. So that's why I think it's very. I mean, it will be helpful if we have some algorithm that can make use the data that lies below this threshold. There is and so I think with my framework, as I said, is one way to make use of the data regardless the confidence measure, and so I guess confidence measure is a method for the very straightforward unsupervised training. But if you applying different methods of semi-supervised learning, not necessarily my method, but also maybe the multi-view learning, meaning that you are able to the one that has lower confidence is not necessary. The one have lower confidence from one recognizer is necessary have the same lower confidence from the other recognizer, another system. So this is where if you combine multiple systems, you are able to find more interesting training transcription that can be complementary useful for different systems. Do you see what I mean?
Yes, yes, good.
Yes.
So all of your plots were the total pot of data was the same size, and you're just sort of changing the tile on labeled versus unlabeled.
Yes.
So what would the plot look like if the pot of labeled data was fixed, and then you had a variable amount of unlabeled data? Would always get monotonically better or
yes,
not?
I have a plot about that. So yes, it's for example, I have a fixed amount of 5% are labeled data, and I try to add the number of the unlabeled data. It like this in our TIMI set, and this is for MIML. And I haven't had a plot made for MINC yet, so I should include it in my thesis.
Any other questions? Okay, let's thank the speaker again.